problem. And that's one of the things that I think captured my imagination first when I first began to get into science, when I was 5, 6, 7 years old. It was the sheer ambition of it, because this is a picture of the universe. This is actually a picture of the night sky. If any of you are interested in astronomy, that thing up there is the constellation of Orion that you can always see in the winter sky. But I want to I want you to focus on a piece of sky that's somewhere around here. I'm going to zoom in on it now. It's a piece of sky that you would cover if you took a 5-pence piece and held it about 25 metres away. So imagine taking a 5-pence piece and putting it 25 metres away over a tiny piece of sky. Well, a few years ago now, the Hubble Space Telescope, which is in orbit around the Earth, turned its gaze to that tiny piece of sky, the 5-pence piece bit of sky, and took a picture. It opened its camera shutter for thousands and thousands and thousands of seconds and just gathered the light from that piece of sky. It was deliberately chosen because it's a dull, uninteresting piece of sky. Actually, from the surface of the Earth, you would see virtually nothing in it at all. But this is the picture that Hubble took. And you see that it's anything but empty. It's called the Hubble Deep Field image. It's one of the most important and fascinating images in the recent history of astronomy. It's not empty. It's got lots of structure, lots of points of light in. There are actually over 10,000 points of light or blobs in that image. And virtually every one of them, over 10,000 of them, are actually galaxies, distant galaxies. So they're not stars, they're galaxies. Now, those galaxies, on average, have, 100,000 million stars like our sun in them, at least. So 100,000 million stars in each one of those 10,000 blobs. The most distant object in that image, and I'm going to talk a bit about how we know these things in a moment, but the most distant object is 13.2 thousand million light years away. It was actually discovered in this image only a few months ago. Now, light travels at 300,000 kilometers per second, 186,000 miles a second. And at that speed, it's taken over 13 billion years to travel from the most distant object in that image to Earth, to the Hubble Space Telescope. Now, when you think that the Earth is only just under 5 billion years old, it means that most of the light from most of the galaxies in that image began its journey to Earth before there was an Earth. And for some of the most distant galaxies there, they were over halfway here when the solar system was just a cloud of gas and dust. It hadn't yet coalesced into the sun and the planets and moons of the solar system. So imagine what that looks like. That's a tiny, remember, 5-pence piece of sky 25 meters away. Imagine what that looks like when you extend it over the entire sky. Well, this is a beautiful map of the observable universe. Every dot on that map is a galaxy, with 100 billion stars like our sun in it, at least. You see that the structure in there, they're not randomly distributed. It's very interesting. I'm going to show right at the end of the talk that we think we're beginning to understand where that structure came from. Just to get some sense of scale, that little line up there, you might not even be able to see it at the back, but that's the 1 billion light year line. So light takes 1 billion years to travel from one end of that line to the other. This is the observable universe. And I'm going to show you, there's a ridiculous number that I have to show you. It's better to show it than say it. This is the number of stars that we think are in the we know from observation are in the observable universe at the moment. 30,000 million stars. Just like our sun, some bigger, some smaller. 350 billion large galaxies, 7,000 billion smaller dwarf galaxies. That's the observable bit of the universe. We have pretty strong evidence now the universe is significantly bigger than that, but we can just see this blob surrounding us, the blob from which light has had chance to travel during the history of the universe. So the universe is big, is what I wanted to say to you. I don't know if you know a comedian called Woody Allen. He once said that the universe is probably infinite, which is a bad thing if you're one of those people who can't remember where they put things. But it's enormous. So how can you... Oh, I don't want to start that yet. There we are. So how can we possibly begin to think about explaining that? How do we know, first of all? How do we know it's so big? How did we find that out from this planet that we're standing on now? And how could we begin to make theories, guesses, I suppose, if you like, about where that came from, how it began, how fast light travels, all those facts that I've said to you, or all those numbers that I've given out that are our best estimate of how the universe works. It is, of course, science. And I wanted to just play you a little video of, for me, what the best definition of science, or the scientific method that I've heard, comes from a very famous physicist called Richard Feynman, who won a Nobel Prize for building one of the first quantum theories of electricity and magnetism. It's called quantum electrodynamics. This is back in the 1940s and 50s. It's our best theory today of how light interacts with matter. But Feynman was also, I recommend that you read his books. He was a brilliant teacher, a brilliant lecturer, as well as a Nobel Prize-winning physicist. And he gave this lecture back in, I think it was the 1960s, and it's just a 1-minute definition of the scientific method.
I'm going to discuss how we would look for a new law. In general, we look for a new law by the following process. First, we guess it. Then we no, don't laugh, that's really true. Then we compute the consequences of the guess to see what, if this is right, if this law that we guessed is right, we see what it would imply, and then we compare those computation results to nature, or we say compare to experiment or experience, compare it directly with observation to see if it works. If it disagrees with experiment, it's wrong. And that simple statement is the key to science. It doesn't make a difference how beautiful your guess is. It doesn't make a difference how smart you are, who made the guess, or what his name is. If it disagrees with experiment, it's wrong. That's all there is to it.
So I think that's a really beautiful description of what science is. It's really very simple. It's the application of common sense in many ways. What it is looking at the universe, looking at nature, guessing about how it works, seeing what the consequences of that guess are, testing those against nature, and as Feynman said, the great power of science. It doesn't matter who you are. There's no such thing as authority in science. If your guess disagrees with nature, then it's wrong, and that's all there is to it. Easy to say, but how can we possibly compare ideas about the origin and evolution of the universe with nature? Well, if you think about it, there's only one way to look into the wider universe from Earth, certainly the universe beyond our solar system, and that's to gather the light from distant stars and planets. And there is an immense amount of information contained within that light. This is our sun. It's a tremendous, I think, video of the sun. This is not a computer graphic. It's a real movie of the sun taken by an orbiting spacecraft that just observes the sun every day. And you see that it's a dynamic and violent place. You could fit 1 million Earths inside that ball of glowing plasma, by the way, 1 million planet Earths. It burns 600 million tons of hydrogen fuel every second into helium. So it's a powerful, gigantic object. Many years ago now, stretching back to Newton and even before, we looked at the light from the sun, and after Newton, we found a way of analysing it by splitting it up into its component colours. So with a prism, essentially making a rainbow of the light from the sun, just as nature makes a rainbow of sunlight using water droplets. And this is a picture, a modern-day picture of that rainbow. Now, rainbows, of course, lots of different colours from blue all the way to red, but when you look at the light from the sun in a laboratory and you're very careful and you put it through a very precise prism, then you see that it's not just an array of colours, it has dark lines in it. All these black lines crisscrossing the rainbow. What those lines are the signatures, the thumbprints, if you want, of the chemical elements themselves. See, what happens is you'll know that an element is a nucleus with electrons going around it. And each element has a different nucleus and a different arrangement of electrons. What happens with the light from stars is that the light shines through elements in the star's atmosphere, so elements like hydrogen and oxygen and helium. And because those elements have different structures of electrons around their nucleus, they absorb different colours of light, very specific colours that correspond to to moving the electrons around in very specific ways. So, for example, these two lines here are very famous. They're called the sodium lines. Sodium absorbs light in the yellow part of the spectrum. If you heat sodium up, it emits light in the yellow part of the spectrum. Why? Because of the way its electrons are arranged around the atom. So what you're seeing here is the signature, the fingerprints of elements in the sun. That's interesting in itself because you can immediately read off what the sun's made of, because you can do an experiment on Earth, see which colours the elements absorb or emit, and you can look in the starlight. You can see what the stars are made of. But also, and this is the point for looking at the wider universe, something very interesting happens when you look at these spectrum, these black lines in the rainbows of the most distant stars and galaxies. So here's a distant galaxy. You can look at the light from that galaxy. What you find, of course, is that the spectrum is the same. The black lines are all the same because chemical elements are the same across the universe, except that in all distant galaxies, the lines are shifted. They're moved. They're not in exactly the same place. Now, one explanation for that, of course, could be that the elements are somehow different in different parts of the universe. But it's interesting, isn't it, that they're all shifted in the same way. And actually, there turns out to be a pattern to this shift. So what's the explanation? Well, the explanation for the shift is very simple. The universe is expanding. So if you look at a very distant galaxy, then you find all the distant galaxies are rushing away from us. Think about what that does to the light. What happens to the light is the light begins its journey from the distant galaxy. Light is a wave. You just imagine a wave on its journey through space. The space is stretching because the universe is expanding as the light journeys from the distant galaxies to us. What does that do? Well, it stretches the light. So the wavelength of the light is stretched. The wavelength is the colour. Red light has got a bigger wavelength than blue light. So as the light, let's say it comes from a star, it's a hydrogen, let's say, emits a line up here, and that journeys across the universe to us, it gets, actually, let's start in the blue. So let's say there's an element down here that emits light in blue. It journeys across the universe, it stretches, it stretches, it stretches. It moves towards the red bit of the spectrum because it gets stretched. And so you see the whole fingerprint of the atoms moved from the blue bit of the spectrum to the red as the light gets stretched, as space stretches. That's what we observe. So that's a very direct measurement that tells us that the universe is expanding. That's one piece of the puzzle. So just qualitatively, you can say that tells us our universe is stretching. Space itself is stretching. How do you quantify that, though? Well, this is, in many ways, even more fascinating. You see, there are certain types of objects, certain types of phenomena that occur out there in the universe that we know the brightness of very accurately. Now, imagine how useful that is. If you know how bright a light is, and you put it somewhere a long way away, and then look and see how bright it looks to you, then you can work out how far away it is. It's very simple. Obviously, it gets dimmer and dimmer the further away it is from you. Now, this is a picture of one of the types of object that we know the brightness of very accurately, and it's actually this one here. Now, this is a beautiful picture. This is the galaxy. So this is an island, as I said, of 100,000 million, perhaps 200,000 million stars like our sun. There are perhaps 1 billion stars in the center of this galaxy, shining brightly. This looks like a star that must be closer to us than that galaxy because it's so bright. It actually isn't. It's actually something called a supernova explosion. This is a star in the galaxy. It's on the edge of the galaxy. It's the same distance away as the 1 billion or so suns in the center and the 100 billion or so stars in the disk. Same distance away, but it's going as brightly as 1 billion suns. How could that be? One star glowing as brightly as 1 billion? Well, it's something called a supernova explosion. It's the death of a massive star, but it's actually a very interesting one. What we think that is, it's called a type 1a supernova. It's something called a white dwarf. So that's the ultimate fate of the sun. It's a star that's burnt out all its fuel and is just sitting there in space, gradually fading away. But it's a white dwarf that had a companion star orbiting around it. Now, the white dwarf, the dying star, sucks matter off the companion star until it gets too big to support itself. Two massive live to support itself, and then it collapses and it explodes. And we know that process very well. It was a process that was predicted actually from quantum mechanics, from our theory of atoms and molecules back in the 1930s. So it's a very specific process, and we can calculate precisely how brightly that explosion should be because we understand the mechanism beautifully. So we know how bright that is. We know how bright it looks because we've taken a picture of it, so we can work out how far it is away. And this is the second bit of evidence you need. So we've got two things now. We've got that you look out into the sky and you see that things are speeding away from us because you can measure the shift in the light. And we know exactly how far those things are because we can look for things like this, supernova explosions in the distant galaxies. Now these are rare. You get on average about one supernova per century per galaxy. So very rare, but there are a lot of galaxies. And this is a beautiful picture, I think, again from the Hubble Space Telescope, which is a picture of galaxies along the bottom as they usually look, and along the top as they looked on a particular day or a particular week when we were looking at them when there was a supernova explosion. So you see here, there's the galaxy as it usually looks, there's a supernova explosion. Galaxy, supernova, galaxy, supernova. Supernova in hundreds of galaxies have been measured, and we've made a map of the universe. We've got the distant galaxies, we know how far away they are, we know how fast they're receding. What happens? Well, I just want to tell you about one specific supernova before I tell you what happens, because it's a fascinating one. As I said, they happen very rarely. A supernova in our galaxy happen on average once every 100 years. The most famous one happened in 1054 AD. This is a picture of it today. It's called the Crab Nebula. You can see it with a small telescope in the sky. It's a beautiful cloud of expanding gas. So this is a star that's died and exploded. 1054 AD, it exploded. How do we know that? Because it was observed by Chinese astronomers, and particularly interesting, I think, and it's one place that I had the pleasure of visiting in one of my TV programs, is this place. It's called Chaco Canyon, which is in the southwestern United States, very close to the Mexican border. There was a civilization here 1,000 years ago that built structures like this, enormous castles and houses in the desert. You see the ruins. You tend to think of or I tended to think in a cliched way about the Native Americans on the plains, riding horses, and you get an impression of what they're like from Western films, cowboys and Indians films. Actually, many of these civilizations were extremely sophisticated and built these giant structures that are still there in the desert. This is in New Mexico, Chaco Canyon. And these people, this is a picture of me, of course, but what's fascinating is not me, but this here, because these people saw that explosion in 1054, we strongly believe, and this is a painting of the explosion, the supernova. Now this was 6,000 light years away, which is a star a long way away from us. But this is a drawing of the crescent moon. This is a drawing of a new star that appeared, glowing as brightly as the moon. And it's thought that this handprint points along, you see it's on an overhang of the rock, points to a place in the sky. And with modern computer simulations, you can wind the sky back to see what it would have looked like on, I think it's July 4th, 1054 AD, when the supernova happened. And you find that indeed, that supernova would have happened next to the moon in exactly that place. At that point in the sky, it would have glowed as brightly, shone as brightly as the moon, and the moon was in that shape, that crescent. So it's a beautiful piece of detective work that tells us that these people, 1,000 years ago, observed a new star shining brightly in the sky for 2 weeks, the Crab supernova explosion. So when you put all that together, what do you get? Well, so we've got lots of distant galaxies, we know how far they are away, we know how fast they're receding. What we find is something called the Hubble law, and it's basically very simple. It says that the further a galaxy is away, the faster it's flying away from us. Now, how are we to interpret that? I mean, you might naively say, well, does that mean we're somehow at the centre of the universe and everything's flying away? Well, no, actually. If you think a little bit more, if you think, for example, about baking bread, if you get a lump of dough and put raisins in it and stick it in the oven, then the bread expands. So all the raisins move away from every other raisin. If you were sat on one raisin, what you would see is the Hubble law, exactly the Hubble law. You'd see the ones close to you moving away more slowly, the ones further away moving away quicker. because the bread is all stretching. All of space is stretching at a constant rate. So you get this fascinating law, which is exactly what we observe. And I wanted to give you the number because it's a very interesting number. I gave a lecture. I don't know if any of you know The Hitchhiker's Guide to the Galaxy. Do any of you know that? Douglas Adams? Yeah, you do. Brilliant. Very good. If you don't know it, you should read it. It's a wonderful, funny, hilarious book. In Hitchhiker's Guide to the Galaxy, it's a very famous number, which is the answer to life, to the universe and everything, and it is the number 42. It's been famous for years. Everyone who knows Douglas Adams knows the number. It does actually turn out remarkably, the Hubble constant can be written like this: 42 miles per second per 3 million light years. What does that mean? It means that for every 3 million light years you go away from the Earth, then things, if you go 3 million light years from Earth, so let's just step 3 million light years away, then on average things will be moving away at 42 miles a second. It's pretty slow, actually. If you go 6 million light years, things will be moving away at 84 miles a second, and so on. So every 3 million light year step you take, you add another 42 miles per second to the recession velocity of things. Now, there's something else, which is actually an exercise you can do if you like doing a bit of maths, and maths, I think, is fun eventually. Not always, but eventually. What you look here is you see this is the distance, right, in miles. I've written it in miles so that I could have 42 there, but you could turn it to kilometres easily enough. So that's a distance. That's a distance, 3 million light years. You could write that down in miles or kilometres as well. It's an easy thing to do. You just type it into your calculator, you can do it. Kilometres cancel out. So the Hubble constant is actually, the units of the Hubble constant are 1 over seconds, right? Because these go away, distance goes away with distance, you've got 1 over seconds. So that implies that maybe you could flip it over, right? You could say, well, so what if that's 1 over seconds and I flip it over, do 1 over the Hubble constant, I get a time. What's that time? Well, that time turns out to be the age of the universe. So you can do it really simply. Convert light years to miles, or convert miles to kilometres and light years to kilometres, cancel them out, flip it over, you get a number. And the number is, with the most accurate modelling we've got today, that one, you'll find that you get something that's of order 14 billion years if you do that sum. Very simple sum to do. Actually, this is the most accurate, I think it's remarkable, the most accurate determination of the age of the universe we have at the moment, 13.73 plus or minus 0.12 billion years. That's a remarkable measurement, isn't it? That's the age of our universe measured by simply looking at the light from the distant galaxies. So I encourage you to have a go at that. You can do it. It's a piece of research you can do. Get the Hubble constant, work out the age of the universe. So that's part of my talk. It's that's how the stuff that I said at the start, how we know it. We know that the universe was very hot and very dense 13.73 billion years ago because we've analysed the light from the distant galaxies. We know it's been expanding and cooling ever since.